Good afternoon, everyone. Welcome to class. As you can see, we will be looking at protection fundamentals. At least we'll be starting that discussion today. But before I get into today's lesson, just a couple of administrative matters that I need to address. Firstly, I I know I spoke about it some time ago, but just to reiterate, because it is a critical matter going forward. That if you are not appropriately registered for the module, right, that well, you know what to do, right? So we are asking that you ensure that you are fully registered to complete this module. All right, so that out of the way. I would have waited a little longer, but I think it's important, especially given that you would have at least started your preparation towards your final assessment. There are a couple of things that occurred in lab number 3. I completed reviewing those lab exercises yesterday, and some of the fundamental points that I needed to be understood coming out of that exercise seem to have eluded quite a few persons. So I thought it's important that I best just speak to some of these matters so that everyone can be on the same page as to what should have come out or what should have been learned from that particular exercise. All right, so the objectives for the lab spoke to the data required for fault studies, and then 2, impact of using star delta transformers on network faults, impact of earthing impedance, and the impact of fault location and severity. Now, in going through the exercise, I know you may not have it before you. However, I was a little forget how it affected me, but I noted that almost the entire class went ahead and did studies on the entire system, especially for the first section where we were finding where you conducted a 3-phase fault, 50% along the Duhaney to Washington Boulevard line. I realized that persons went as far as doing those studies for the entire system. Now, just from a research standpoint, if we want to determine the impact of a certain input, yes, then it wouldn't be sound research or experimental technique to be making several changes or to be having adjustments to several inputs simultaneously, which is why I asked you to focus on this particular line, nothing else, just this line. And so my reference, for example, where it says that that you should display the results on the figure as I had done, and then I indicated that the actual fault current was shown in the table. The only reason for me doing that was to allow you to know whether or not the network that you had in place was accurate. So in other words, I simulated the fault, I noted the values, and the only thing you needed to do was to look at that table, note that the currents as described in that table were similar to yours. So you now know that you have satisfied the requirements to go forward. So my expectation was really that all the assessments or the evaluation up to point 4, yes, up to item 4, would have been about the Dehaney Park to Washington Boulevard line, because I needed you to understand or appreciate the impact of um, the fault going closer to bus bars. Yes, so we were just experimenting on that line. So that first section where I think persons used in some instances 4 or 5 pages of results, telling me about all the lines that were there, was totally unnecessary. Now, this may be a matter of interpretation, but it concerned me because I don't know if it is an issue with how I communicate, um, you know. But there was I read this document several times, and I am unable to see where the misunderstanding would have occurred. But if you misunderstood the instruction, and the reasons why you misunderstood it, I would really appreciate hearing that from you, so that I can improve my communication techniques going forward. But for what it's worth, it in my estimation caused persons to do a lot more work than was necessary. All right. So as I said, if you do have, or if you did misunderstand that, I'd like to understand why it is that you took the interpretation, or why you had that interpretation of the instruction. Um, and so point 5 then went on to speak about doing the tests on the bus bars to determine which one of them had the highest 3 fears. And this student was a follow-up from what you would have done up to point 4, because by the time you completed part 4, you would have recognized that the highest fault currents would have occurred at the bus bars. So it is really in the substations or at the bus bars that we would do our analysis. We don't simulate faults in the middle in order to determine severity. It's really at the substation, or in other words, at the bus bars that we do that. So having gone through that exercise, you would now come to 5, where you are looking at the type of fault and the fact that, whether it was the double line to ground or the line to ground, which was creating the largest fault simply because of the configuration of the network. So did anyone, as I said, if you misunderstood, I really need to hear from you. All right. It's not going to affect the mark one way or the other, because we have already marked them. So the conclusion that would have been arrived at is that the fault is more severe at the bus bars. Right? Some persons say, well, at 0 and 100%. But that was just a way of getting you to do the tests. But the concluding statement was that the faults are most severe at bus bars. Also, with the earthing impedance, I think most persons figured that one out, that it's going to impact your ground related faults. So you're line to line to ground and you're line to ground. And also as you increase the impedance, you're going to reduce the fault current. And some persons did do a fairly good job in terms of the theory, where they explain that whilst we try to reduce, or you may solidly ground a transformer, but you don't want to do that for the generator because um, in doing so, the high fault current that will flow through can easily damage the generator. So we earth run impedance to reduce the current flowing through, the fault current flowing through the windings of your generator. But of course, that has to be managed, and one will expand on that from a protection standpoint. So, in terms of the objectives, one, the fault is more severe at the bus bars. Earthing impedance reduces your fault current. Star delta transformers sectionalize your networks, and most persons went through the whole business of you know ensuring that the zero sequence, because zero sequence current can't flow with the delta or the star. And I was disappointed that many persons were still just talking about star instead of grounded star. But enough individuals mentioned the fact that it's a grounded star. So I was comfortable with that. And the first objective regarding the data required, um, part of the reason I needed you to focus just on that particular line is that what you would have recognized from early on, when you put the zero sequence and the negative sequence values to zero and ran that three-phase fault, you still got the same value, which is saying to you that the symmetrical fault uses um, only positive sequence impedances as part of the calculation. So, as a concluding statement, because we're asking that what data is required for faults, the data that is required for symmetrical faults would be your positive sequence information. Yes, positive sequence for your line, etc., etc., etc. However, once you are dealing with an unsymmetrical fault, you require positive, negative, and zero sequence information. And those are the concluding statements that I was expecting. All right. So those are the findings that you should have had from your lab exercise. All right. I'll pause here. Any questions or comments?
Honestly, sir, I just think it
I didn't hear that clearly. All right. Well, no questions, no comments. I'll just move on then. All right. Now, as I said before, we are gonna start looking at power system protection fundamentals. But if you look at your syllabus, you would have seen some in between substation. I think the substation fundamentals. You would have had under that. You would have had smart grid and microgrids. Yes. So again, if you go back to your module outline, it says that you would have done 5 lab exercises. All right. So in lieu of the 5th one, which I think it was grid interconnection, right? I'm going to ask that you do a very well. You decide if it's short, but I want you to complete this assignment, and it's an individual assignment. It's not a group assignment. It's an individual assignment which would form part of your lab grade. All right. So the assignment is shown. You can write it down, or you can wait on the recording and go back through it. So to state the summit, please. All right, we're finished with this. Next. So here is the real activity for you. Now, students, I want to make it abundantly clear because I realize that you have all been ignoring. Well, no, I withdraw that. That's an inaccurate statement. Many of you have been ignoring the pH stipulation for your labs. And quite frankly, in most instances, when I see 18 and 20 pages, it's usually when I'm getting information that is unnecessary. For example, I saw one lab yesterday with 22 pages. However, in the results, all the results were repeated. So I got the result, they gave me the information in a table, and then they gave me the same information as a bar chart. And the table and the bar chart took up 1 page. I decided I would not penalize you, but please. I said 3 pages. Right? I said 3 pages here, and that is exactly what I mean. If you give me 4 pages, I'm reading the first 3. And whatever information is contained in those first 3, that is what I'm going to run with. And of course, you are expected to put all your diagrams, etc., in those 3 pages. Okay? So I don't want, a whole thesis on smart grid. Read and provide me with the important details. At the same time, I'm not telling you to try and squash everything in 2 paragraphs. You give me 2 paragraphs, I give you the value of 2 paragraphs, all right?
Excuse me, sir.
Yes.
Some lecturers include the cover page in the page requirements. Is that the case here?
Are you reading the slide?
Yes, sir.
What does it say?
My bad, sir.
Huh? You are now seeing it?
Yes, sir.
All right, good. While you're writing this, I have been challenged in terms of, and since, was that Mr. Burns? Since he raised the thing of other lecturers, because I don't know if I am, well, I haven't really penalized you, but I don't want to penalize you when you are being taught something else, but then you come to me and present it, right? Because I am also an employee of the university. So if you are told an incorrect in one place, the best I should do at this level is to correct it. But help me, students, especially the year 4 students who are doing or have done research methods. In terms of captioning, is it that you were taught somewhere that you caption a table below the table? Anybody?
No, sir.
Huh?
No, sir. Above.
You're taught to caption it above.
Above. Yes, sir.
The tables you're referring to, sir?
Yes, tables.
Yes, sir.
All right. It's these things are a bit of a concern, and I say it against the background that when we speak to or engage with employers, one of the reasons that some of our graduates technically savvy, they know the thing, they can do the thing. But in terms of presenting the work or presenting a report, they fall down. And I saw there are a couple groups, but there is one group in particular that I have made the same correction on every single lab that I have assessed so far. I recall I told you not to submit lab 2 until I was finished marking lab 1 because you needed to see some of the things that I was marking for. And I got back the same error, captioning below, and I would draw the arrow and say put it at the top. And it came back in lab 2 and it came back in lab 3. You know, these are things are a little disturbing for me, not just as your lecturer, but you know, as an administrator at the institution. It is of concern. The other issue, I mean, the horse kind of gone through the gate now, but the other issue is that you're writing a report. It's a lab report. How can you be writing a lab report in the present tense? Yes, students, I know you may not have had this type of assessment from others, but I do actually sit down and read your labs. You know, it took me close to, 11 hours yesterday to mark them, but I read them. And it's important that, we make the adjustments before we go through the gate. Okay? So coming back to this, no more than 3 pages, and you see what I want from you. All right. Any questions, concerns, anything you want clarified before we get started? Now is the time. All right, so let's get into protection. Protection fundamentals. Now, I've gotten all the fancy definitions regarding fault or faults, and these definitions are, an abnormal operating condition, etc., etc., etc. So we know the fancy definition. And when we talk about protection, and in this case, we're dealing with power system protection. The graphic here talks about the wild power system. Because out here, in this power system, there are just so many things that can happen. And as the designer of this power system and the operator, we need to be cognizant of some of these things. So what I've done here is just to list a couple items or a couple things that can happen within your power system. And when I speak of the power system here, I'm dealing with the entire, from generation, transmission, distribution. I'm talking about the entire system. There are several things that can happen. I mean, we're dealing with synchronous machines. And so we recognize that you need your field, and that field can be lost. All right? You can have overexcitation, which means that it's going to impact your voltage. On the back end, we have our turbine here, yeah? And we are saying that in terms of it being your prime mover, it may get to a point where it is driving the generator beyond what it should, yes? Because of course, whatever output we get from the generator, whatever power output we get from the generator, is the power coming from the prime mover. The generator in of itself, per se, does not create its own power. So it's the mechanical power from your prime mover that produces that electrical power. All right. So in that, depending on the speed, it can cause frequency issues. We can have retardation issues. From the circuit breaker, you can have the breaker failing. You we haven't looked at it, but I'm happy that some persons in their theory discussed it. Yes, we have not spoken a lot about open circuit faults. We have looked primarily at short circuits, simply because they are the more severe, and we are not really seeking to delve a whole lot into power systems. But the point is, we can have open circuits, and with those open circuits, yes, with those open circuits, you are going to then end up with the frequency issues that we just mentioned. You can have issues with the generator, issues with the shaft, and so if we have shaft issues, you might get excessive vibration. So we have to monitor that. And so I've given you all of this. Yes, all of this that's happening on this side of the equation, and it's going to manifest itself on this side. And as the engineer, we have to find a way to address all these abnormal conditions. So power system protection tries to anticipate all the issues that may occur within your power system, and then provide ways of mitigating against these, right? To reduce their negative impact on the customer. All right. So in essence, that's what it's all about. All right. So by definition, it deals with quick isolation of equipment operating abnormally, right? Or isolation of problem areas. But whilst that is key, it is also important that it allows the rest of the system to continue operating. And I usually use as reference, because it is something that I believe everybody can identify with. At home, you have your circuit breakers, yes? You have your distribution panel. Within that distribution panel, depending on the number of ways you have there, let's say I have a 16-way panel. So you have 14 circuits coming inside there. To, of course, use for your supply. If you have a fault in the living room, you would want just the breaker that handles, and if it's a fault that's associated with the plugs, you would just want the breaker that deals with the plug for the living room to trip. And that breaker, when it trips, only the living room will be out of service. However, if that breaker malfunctions, and for whatever reason it does not trip, then what is going to happen is that the fault will now move from just being limited to the living room. That fault will now be a part of the distribution panel. And so instead of just one breaker tripping, the main breaker will trip. And so all the breakers within the panel would lose power. The same principle is applied to your power system. Meaning, when that single breaker trip, what it is doing is to isolate. This is your living room. Well, so it isolates the section of the house that has an abnormal condition, yes, or is the problem area. But at the same time, you still have power in the kitchen. Yes. You still have power in the bedrooms. You still have power in the bathroom. You have power in the rest of the house. But the problem area is isolated. With your power system, with your protection for your power system, it seeks to isolate the areas that are causing the problem, but at the same time tries to maintain power or supply to the areas that are operating normally. Okay, and that is key. It is not just about identifying the problem and isolating. A critical component is that the rest of the system is allowed to operate. All right. Now, I said earlier that if the breaker does not trip quickly enough, then it's going to cause the fault to escalate. But also, if it doesn't trip quick enough, then you may end up with some damage. So whatever was causing the problem, whatever was causing the problem, we have the possibility of damage of that equipment or, possibility of fire. So the systems will always seek to minimize the duration. So you want to identify the problem, identify what is causing the problem, and you want to get rid of it as quickly as possible. But whilst you're doing it quickly, you want to ensure, yes, that you're doing it correctly. So you can't be fast and foolish. You're fast, but you want to do it accurately. And I use the same story I have been telling for years. Well, I need to recognize that most of you would not even know who Patrick Patterson is, because you're all so young. But anyway, he was one of the fast bowlers here in Jamaica. They had Patterson, Walsh, and Olin. Right. Patterson was very fast. But when Patterson was bowling, many times, instead of the wicket keeper collecting the ball, maybe the guy at second slip end up collecting it because he's spearing the ball over the place, all over the place. He was fast. He was the fastest among the bowlers, but he was foolish. The power system protection mechanism must be fast, but it must be accurate. So we want to do it as quickly as possible. So think about it. I don't know if you have ever done anything at home that caused the breaker to trip. Yes. And if you haven't, then you should not be doing electrical engineering. Right? You must have created a problem at home already. Because anyway, I'm not telling you to burn down your people in the house, so let me leave that one alone. But it happens quickly, right? And it limits damage and outage time. So whatever protection is used, it must operate quick. It must limit any possibility of damage, yes. And the persons or the area that is isolated, you want to get it back into operation as quickly as possible. Bear in mind that the objective of the utility is not for you to be without power, because they are actually selling you that energy. So if you don't have power, then they can't earn. So the objective of the utility company is to provide you with electricity as much as possible, because unless you are using it, they don't earn. So in terms of the protection systems, yes, these are the four critical steps that are involved. All right. The first one is that we need to be able to detect the abnormality. So we want to detect the condition, the abnormal condition. All right. Secondly, want to process the information. Having detected it, you need to make a decision as to what is it? What is the real problem? And then thirdly, you want to make a decision. Do I need to isolate? Do I need to just alert someone? All right. So after you have processed the information, the decision will be made to separate the problem area. Yes. Or you may send out a warning. And then finally, we have isolation. Okay. Now these four steps utilizes different pieces of equipment, and we're going to talk about a few of them. I know this is introductory, so we won't go into them as detailed as I would have done with protection students. Right? But just not to lose the point, the processes, yes, require certain types of equipment. So we start by looking at how we go about detecting that there's something wrong. Right? What do we, there's a fault. How do I know that there's a fault? Where do I get that information from? And so detection utilizes your current transformers, your voltage transformers, the lightning arresters, of course, your relays. Somebody trying to say something? Yes, Senator? No.
Terrible, that's it.
Now, in terms of your current transformers, we'll be able to detect currents at different levels. Of course, what it will be doing is just faithfully transferring whatever current is on the system. It's going to give a scaled replica of that. Same thing with the voltage transformer. Yes. Now, I suppose there can be some debate as to whether the lightning arrestor really detects or whether it processes. But really and truly, it's going to detect as well as process. And similarly, the relay. So you want to provide an input to the relay. Yeah, the relay is going to detect it, and the relay is also going to process it. But detection of abnormalities uses these equipment. Now, in terms of processing, what we focus on is really the types of systems that are involved in processing. And by that, yes, I'm talking about whether you're going to process it by a differential system, meaning looking at the input and the output and determining if there is a difference. Right? That's basically what differential is about. Or distance, meaning find a way to determine, for example, on a transmission line, we want to determine where on the line, how far from the bus bar the fault is located. And we use our distance protection to do that. Or overcurrent. Now the breakers at home are primarily overcurrent. Yes? Meaning, if the current exceeds a particular value. Yeah? But not only if it exceeds a particular value, but it is also given a time consideration. So for the overcurrent, it's whether it exceeds it and for how long. Okay? And then finally, we talk about. By the way, in terms of the initiation, the processing and initiation that would take place in terms of the relays that would be part of these systems. All right. And then for isolation, we're talking about breakers and fuses. All right. So in terms of well, and I know I'm sort of dipping into the protection module, but the module itself follows what we have here. In other words, we're going to be looking at the detection of abnormal conditions. So we are going to be looking at these hardware that's used in your protection. Yeah. And then we would move to how we go about processing the information that we get from these hardware. Yeah? And it takes into consideration, DSP, etc., etc. All right. Sorry. Okay. All right. So we would look at these schemes and how they operate. Yeah. And then finally, we talk a little about the isolation. We talk about the breakers. We talk about the fuses, etc., etc. All right. So let us jump into some classic definitions. Yes. As it relates to your protection system. All right. Okay. So we start by talking about just looking at some basic concepts. So when I talk about your protective gear, what I mean by protective gear? Simply put, that's the equipment we use for detecting, locating, and initiating the removal of a fault from the power system. So in other words, everything up to the decision and action to initiate removal, all the equipment up to that point constitutes your protective gear. All right. So in other words, the breaker would not be part of your protective gear. And we'll talk about that later. Okay. So the equipment that would be listed under this, under protective gear would be your relays, your current transformers or CTs, your voltage transformers, and note I put potential transformers here because depending on the literature that you are reading, if it's a little dated, then it would refer to voltage transformers as potential transformers. So you see there as PTs. All right. But for us, we look at VTs. Right? Same thing. Your shunts, your DC and AC wiring, and any other device relating to the protection relay. All right. So these constitute your protective gear. And then remember what I said at the beginning. What we want is that we want to isolate, we want to detect the problem and want to deal with it quickly. So there are some keywords that comes as part of the protection discussion that we have to look at. Okay? Any questions so far?
Not really, sir.
So to fulfill the requirements of what we call discriminative protection, because this is one instance in where discrimination is a positive thing. All right. So we want to have discriminative protection, and this must be done at the optimum speed. We want to do it as fast as possible. So you want to discriminate, and you want to discriminate quickly. Huh? Now, to achieve these objectives, it's going to be dependent on, the configuration, the operating conditions, the construction features of your power systems. Yes, it's going to be critical. It's going to be critical that in achieving this fast discrimination, that we look at relays, different types of relays, which will respond to different aspects of the power system. So for example, remember earlier I mentioned that one of the issues that you may have in a power system may be a frequency issue. Now, do we have a frequency relay? Yes. Is it really measuring frequency? No. What it is really measuring is voltage. So we measure the voltage, and that gives us an indication of what's happening to the frequency. I mentioned earlier that you may have an issue with the shaft of your generator. Can you stop the generator to see what's happening to the shaft? Absolutely not. All right. But do you need to know whether or not everything is okay with the shaft of the generator? Absolutely. What do I do? So I need to find a relay that can measure the level of vibration. Because if there's an issue with the shaft, that shaft running at that high speed, even with a hairline fracture, you will start feeling the vibration. Right? I know that might sound crazy to some persons, because if you have been around a large generator, the place is noisy and the place is, in many instances, always shaking. But the fact is, once you have an issue, that relay would be able to detect it and provide you with some warning, or separate or shut down the generator, depending on what settings you would have made for it. So as I said, you have relays that respond to different aspects of the power system. And the aspects that we refer to here include power. So you may have relays that respond to power. You have relays that respond to impedance or measure impedance. Some of them looks just at the magnitude of the current, frequency, and I mentioned earlier, vibration. Right? Now, I hope by now you'd appreciate that how I protect a transformer would therefore be quite different from how I protect a generator. We spoke earlier about the earthing impedance. The generator, I don't want to have it solidly earthed, because if I have an earth fault, the current that is going to pass through that generator, may render the generator useless after. So I want to limit the current that goes through the generator coils. But at the same time, I need a current large enough that will operate the relays. All right? Because remember, we want to ensure that we operate quickly. Very important. All right? So we have different systems. So you'll have a system for your transformer, you'll have one for your generator, you'll have one for your line, you'll have one for your you name it. Right? However, these systems Yes, we can't have them operating. Well, in some instances, they operate independent of each other, but you can't have the if you have a fault on the transformer somewhere in Wool Harbor, it's going to cause the generator in Hunts Bay to shut down. You can't have that, right? So we have some further definitions that we have to understand. So the individual protection arrangement. So when I protect the transformer, that's known as a protection system. Yes. When I put everything together, and coordinate everything, and that's referred to as a protection scheme. So the individual arrangement, looking at a transformer, looking at a generator, look at a motor, these are protection systems. That's just a system. When I coordinate everything and, understand how they interface with each other, that's my scheme. Are we clear? All right, so in essence, that's it for protection gear. Yes. And then the last thing we want to mention, because we said there is protection gear, but there's also what we refer to as switch gear. And the switch gear would therefore be your breaker. All right. So the main switch gear, it's very important, but it is not a part of what we refer to as a protection gear. Okay? All right. Now, just to move us further into some of these fundamental principles, we're going to take some definitions, some basic definitions that are used in protection. I don't want you to think that well, let me not preface it that way. Let's just get into the definitions. Let's start with reliability. What does reliability mean? We want the system to operate when required. So, my big question is, how often do the circuit breakers in your home operate? Anybody? When was the last time a breaker in your house tripped?
Sir, I think me have experienced that, sir.
I haven't experienced it, and that's good. All right? So the question is, how you know it's working? So Adams?
Sir, I don't know if it's working or not, sir. Probably they would have to test it, sir.
Yeah. And therein lies the challenge with your protection system. We say it is reliable. All right. So one key feature is reliability. And that speaks to the system being able to operate when you need it. Now, you may have a protection system that is designed and that will cost you millions of dollars. Yes? And that system will never operate. However, if the need arises, it must operate. So there are things that you're going to have to do to ensure that your system is reliable. All right? I mean, you can't go around simulating. You see, you use Power World, and for some persons we may introduce it to ERAX, but you have Power World, and you can simulate. I tell people you can't blow up anything in Power World, right? But you can come out and go simulate on the system. You can test the system. You can go put a fault on the system to see whether or not the breaker works. Right? But that reliability, students, that reliability is dependent on some key aspects of your protection system. Right? And these include the design of your protection system, the installation of that system, and of course, deterioration. Just like when you think of deterioration, I mean, you buy a brand new car and once you drive it off the lot, it has depreciated. You know, once you have installed your protection system, yeah, once you have put it into service, it's gonna start deteriorating. Whether it is from the elements, you know, some things you just can't prevent. You know, we're dealing with, and when we spoke about substations, we talk about indoor and outdoor substations. The outdoor ones exposed to the elements. You know, the protection system may not necessarily fully interface with that, but we're gonna have issues. All right, you're gonna have some corrosion, you name it. You're gonna have these challenges. So what we're gonna do is just to look at each of these and see how they impact reliability and how we can go about mitigating against these. So we start with the system design. Now, you have some bright engineers. And in this class, you have some bright people. And it is good to be bright, don't get me wrong. We'll go out there and we'll go and design some systems that only us and the technician that worked with us understand. We're immediately putting the company at risk. So we can have the fancy designs. We can put in the designs, you know, 25th century designs, right? But the bottom line is we need to ensure that we understand. Right? Now, the power system itself, you have to understand that in order to, you know, design your protection. Now, and I hope I'm not, well, you know, let me leave that one. The bottom line is some of the things that we have done in power systems, all right? We're going to have to do it again. So if we're going to do protection, there are a couple of things that we sort of just gave you gave you a piece. We're going to have to give it a whole of it before we can continue into protection. So even with the fault analysis that you have done, you know, we have to go back through that and massage it a bit. Because you have to understand how the system operates. Right? The issues we just pointed out earlier, for example, and we're talking about understanding the system before we can do the design for the protection. What we spoke about in your lab, or what you did in the lab by looking at earthing impedance, you have to understand that before you can come and then design the protection for the generator. I saw a person talking about earthing transformers in the lab. And, you know, I'm not going to fault anybody. You know, you have done the reading, you have some information. But you have to understand the information before, you know, it's good to try and really understand this stuff before you come and present it. All right? So that's the bottom line. You have to understand how the system works before you design. And in that design, you want to make sure that the design is adequate You also want to make sure that it is simple. Yes. So that persons who will come after you will also be able to troubleshoot and quickly understand the operation of the system that has been designed. Okay? So I don't want you to go out there in industry and operate like you're in Dexter's lab. All right? You want to make sure that it is capable of doing that which it is being designed to accomplish. All right, next, installation. You want to keep it simple. All right. And what Mr. Adams said earlier, in terms of him not recalling seeing a breaker in his own stripping, the only way you're going to ensure that although you have not seen the breaker tripping, that the breaker will work, you have to carry out some tests. Now, it is easy for us to go and flick the brake a couple times, make sure that when you turn it off, it go all the way back, and you actually can feel that the spring is okay. All right, so you flick it and you push it back, and you must get you must have that force against your finger when you're closing it, so say it all right. So you do those checks. The same thing is true. You're going to have to do some troubleshooting. You're going to have to check your protection system, and part of being able to do that check is to ensure that it is installed properly. Right? And then finally, deterioration. As I said, after installation, deterioration will take place and could interfere with correct functioning. And you have to ensure that you do routine testing. Yes. Now, I give you this because in one instance, we have had a past student of this institution who was responsible for one of the All Island blackouts. Part of the reason he didn't carry out the maintenance activities that were required. Now, it wasn't totally his fault, but the reality is he was responsible. The boss wasn't following through with what he required, and he just went and sat on his hands. And when the fault occurred, the breaker that he should have serviced did not operate. Yep. And so he and his job, they had a tumultuous relationship thereafter. They couldn't stay together. So he had to separate himself from the job. But that said, you as students need to recognize the importance of these things. All right? You have to do your maintenance. There's one other person who was associated with the institution where his responsibility was for the batteries. There are some batteries that are in what we call the relay house. Right? He had that responsibility. There was a fault, but the relays couldn't operate because the batteries were dead. Why? No maintenance. All right. So there are things that are routine that we do, and like Mr. Adams, you never see the breaker trip yet, so hey, we never had a problem. But still my boss telling me to go check this and check that. Listen, you go check it, and you make sure that you carry out those preventative maintenance activities. All right. Any questions, any comments? All right, I'm gonna ask that we just pause here for a moment. I'll be back in a minute. let's address something outside. Listen. All right. So continuing with definitions, we talk about selectivity. Yes. And selectivity deals with the ability to remove or isolate a particular section of the network. Yes. Now I know that that may sound quite similar to discrimination, as we mentioned earlier. And we'll soon highlight the difference between the two. So selectivity is based on what we call time graded, or unit systems. Now, your time graded systems can we move on? Your time graded systems works in such a way that we have what are known as protective zones. And these zones are arranged to operate in times which are graded through the sequence of equipment. Now, what does that really mean? I would break up a network into different zones, right? And I'll just highlight that in terms of the zones in a few minutes. But your zones really consists of the equipment being protected, and it is bound. It is bound by the relays that feed information to the breaker that will isolate that particular piece of equipment. What does that really mean? I'm just gonna quickly go down to the figure. Right? So these are what we refer to as zones. So as I just mentioned, you have here, this is a line, it's that transmission line. Okay? And these would be the breakers associated with that line. So if we're removing that line, then we'd open the breaker on either side. All right? Now, what we have, this dotted line is going through the relays that would control these breakers. So that's why it goes beyond the breaker. Are you with me? So this would be a zone. Let's look at, so here's a transformer. Let me use a different color. So here's a transformer. These are the breakers associated with the transformer. So the zone is the transformer and the switch gear, but it goes through the relays that controls that breaker. All right. So I'm going to look on the on this side. All right, looking on that side. And since the zones aren't shown over there, I'll just put it in. So again, here is my generator. Here's the breaker that's associated with the generator. So this zone would go through here. So it would include the switch gear, which would be the breaker, and it goes through the relay. So it goes beyond it. I mean, you don't have to stress yourself over that right now. You know, if you choose to come up to protection, then we'll discuss this a little more. So in terms of your transformer, that would be a zone. This would be the zone for this line. All right, get the picture? Anybody who is not clear on what I'm doing?
So I get the picture, sir.
So the term graded systems, what it is saying is that, let us say a fault let us say a fault occurs on this bus bar. All right, so the fault is on this bus bar, even though, you know, let me change that. Because if you note, this bus bar is sectionalized. Remember we're talking about the sectionalized bus when we're looking at substation fundamentals. So this is the breaker, and it breaks the bus bar into two. So that's why you have this zone for the bus bar. So I'm saying, let's go back to what I was saying. So you have this fault, and it's on that bus bar. So you have that, all right? Now, what we're saying, you know, let me give you something simple. Let us say the fault is on this generator. Note that the generator zone overlaps the zone for the bus bar. So this is the generator zone. And this is the bus bar zone. So they overlap. All right? Now, for a time-graded system, what we are in effect saying is that if the fault occurs on the generator and the generator breaker, so this breaker that is inside here, what other color can I use? So this breaker that is right there does not operate. Then the other breakers associated with the bus, which would be this, 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 and this, because they are all breakers associated with the bus. Those breakers will operate, but they will only operate after a certain time because the main breaker for the generator has not operated. All right, remember, fundamental. I know it was a simple statement, but it is fundamental to your understanding of road system protection. Is that in isolating any part of the network, the key objective is that we want to limit the extent to which customers are going to lose power. Or in other words, we want to limit the area that is isolated. So you want to get rid of the smallest area possible. Okay? So time graded system. But yeah. So coming back to this, it says once a fault occurs, although a number of them will respond, only those relevant to the faulty zone complete the tripping function. So as I said earlier, the breaker associated with the generator would be the one that should trip based on what we have here. That's the relevant breaker. However, if it doesn't trip in time, so if it doesn't trip fast enough, because it is now impacting another zone, the breakers in the other zone would then trip and isolate not only the generator, but if we go back here, we would have lost the fight, because if all those breakers trip, then this transformer would be out, this line will be out, that line will be out, it would separate from this section of the bus bar, right? So you get the picture. If the local doesn't trip, then it's going to take out more of the system than is necessary. But I don't want to carry you into all of that detail just yet. Now, this is another thing that we need to have clear in our minds. Although I had that fault on the generator, all the breakers, or all the relays, sorry, not the breakers, all the relays in the power system would detect the abnormality. Right? Now, if the generator breaker operates, then the other relays will make what we call incomplete operations and reset. So in other words, if the local breaker takes care of the problem, they will say, okay, fine, problem is taken care of, we'll continue to operate and keep the system intact. But if the assigned breaker does not operate, then it means that they will operate and more of the system will be lost. Okay? All right. So we talk about time graded, so that they are based on determining whether or not the relevant breaker will operate. That's time graded. Good? But there are times when we can't wait on anything. We can't wait to see what is going to happen. We call those unit systems. All right? And unit systems, they respond to faults within a clearly defined zone. They do not coordinate with anything else. Once the fault occurs, they trip. They ask no question. So earlier we spoke about the type of protection systems or the methods of protection. Remember we talked about distance protection or differential protection. What we are saying here, like differential protection, it is looking at what's coming in and what's going out. If what is coming in is not equal to what is going out, and it passes a certain threshold, trip. So it doesn't ask any other question, it looks at what's coming in, it looks at what's going out. If the difference is large enough, it operates. Right? That's the unit protection. And it can be applied anywhere. Okay? But the time graded, where it is looking at what's happening with A and seeing how long A is taken, then it decides the trip. That's your time graded. All right. And then I spoke about it, but I didn't give you the formal definition for zones. All right. So you have that here. Don't worry, we'll soon be done. So we said that a zone, a protection zone, is a piece of equipment. Yes. And I did say bounded by the relays that controls the breakers. More simply put, it's just the piece of equipment, inclusive of the switch gear associated with it. All right. So in the case of this network, we have the equipment. So here we have a transmission line, and these are the breakers associated with the line. We have a transformer. These are the breakers associated with the transformer. So that's a zone. The generator and the breaker, that's a zone. The line, that's a zone. The bus bar and all the breakers, that's a zone. Okay? But again, this is just introduction. We're not asking you to be able to identify zones. All right, continuing with the definitions. Talk about stability. All right. Now, earlier I just said to you that when we have a fault on a piece of equipment, that all the breakers in the system, all the relays, I keep saying breakers, all the relays in the system detect it. However, only the one that is associated with the equipment should operate. What stability is saying is that the protection system should be non-responsive to all load and fall conditions outside of the zone. Yes? And that now speaks to your time graded, right? And this is where the difference that I mentioned earlier, yes? We're talking about selectivity, yes? And you know, its similarity to discrimination, but one deals with your time graded system, one deals with your unit system. Okay? Are we clear? Or maybe that's the wrong question. The right question is, should be, are we awake? Anyway.
Yes, sir.
Yes, sir.
Yes, sir.
So speed. So we talk about stability. And as I said, it deals with the ability to remain non-responsive to load and fall conditions outside of the protection zone. Yes? And then speed, how fast can we isolate? Now, the terms that I'm using here, and again, we did talk about the workings of synchronism, and we're looking at integration, renewable system integration, right? Now, we must be fast enough to prevent loss of synchronism. Now, I'm trying to find out how best to explain this without getting into too much detail. The bottom line is when you have a fault on a system, it's going to impact your generating unit. So your generating unit may start to export more power than it needs to. It could be a loss of load. So a loss of load, depending on how significant that load is, can cause your generator to overspeed. The easiest way to explain this, sir, in my head, the best way to explain this is if you have ever listened to a standby generator, all right, where the generator is running, and if you were to go and let's say turn on the microwave, you might hear the generator. It gets a little dull, so it slows down. Okay, but at the same time, when you then turn off the microwave, it gets high because it speeds up. Okay, now depending on that change, and I'm thinking now of a large industry. Remember earlier we spoke about the fact that the flour mills has its own feeder, right? Now, if for whatever reason the flour mills is in full production, full production, and they are pulling maximum power from JPS, and then suddenly it trips, that's a significant loss of load, right? Now, if you lose that load just like that, it's going to affect those generating units out by Rockford. And what I'm getting to is that the generator has what we call a critical clearing time, meaning that you must deal with this matter, whether it is to clear the fault or deal with the loss of load quickly. Because if you do not deal with it before this critical time passes, then the generator is going to lose synchronism. In other words, and if you go back, well, I know you don't have it. Well, I gave you the figures already, but the loss of synchronism that we mentioned as one of the abnormal conditions on the system. If we lose synchronism with one unit, it's going to put pressure on the other generating units in the system. So losing a major unit can cause all the other units to pull out, and then you may end up with an all-island blackout, as we have experienced in the past. Yes? So the point we're making here is that your protection system must be, or let me say, in designing your protection system, you must be cognizant of that, because the fault cannot remain on the system beyond the critical clearing time, because that critical clearing time that you have calculated, yes, is what you would use to represent the maximum, or should I say, the limit in terms of operation of your protection system to clear whatever fault there is. Okay? So that's where speed comes in. And in doing it quickly, you prevent the loss of synchronization. All right? Or synchronism, what am I talking about? All right? As I said earlier, speed is important, but it must not be sacrificed for correct operation. But I'm not saying, oh Lord, I am not saying that you must say, well, I am getting it right, and therefore I can go as slow as I wish to. Right? You have to understand that, yes, you have to do it quickly, but you have to do it accurately. I suppose that sounds like my exams, right? Sensitivity. This refers to the magnitude of the current required to operate the system. Go back to what we said about earthing impedance on your generator. You want to ensure that you reduce the current going through the generator. yes, by putting in the earthing impedance. But it cannot be so low, right? You cannot reduce the current to that point where it is not large enough to effectively operate the relay in a fast enough time. All right? So it's a lot of considerations. And why I love protection, and I don't know if you get the sense already that I really love it. All right? I love protection because there is a lot of art to the science. You have to understand the power system. You have to understand the numbers. But having understood the numbers, you then have to, think it through and come up with practical solutions. Right? It's not just some mathematical formula that you are given, and then you just plug in the numbers and you're good. No, it doesn't work like that. All right. And then we want to talk about, primary and backup protection. There are some parts of the system that requires you to deliberately, right? You have to be deliberate about putting in secondary or even tertiary protection schemes. All right? So you have to put a protection scheme on top of what you have implemented. Right? So for use of a better word, you're gonna put in some just in case protection. So you have a protection system scheme that is operating, but you have one on top of that. Right? And as I said, you have to deliberately go in and put in the second layer of protection, or even third layer of protection. But there are some systems that you will use that inherent as part of their design, you get backup. Right? And we need to also make the point that, depending on how important the circuit is, that will dictate whether or not you do secondary or tertiary. Right? I may have said this to you, but there is total redundancy of the transmission network in the UK. And I just feel so them just have a world for money and this. Anyway, maybe it's grudge them. But there is total redundancy in the UK, meaning that wherever there's a 400 kV line, there is one running right beside it. And each carries secondary protection. So that's how important it is. I remember several years ago, I think it was after the London bombing. Don't hold me to that, but I think it was. When they had a power outage in London, I mean, it was the strangest thing to these people because they don't know what power cuts are. And we can't power cut in London. Right? So, depending on how important, you may want to increase the protection. So, you can take that as a principle, whether you're working with a company or you end up working with a utility. Yes, that the protection system, you can double up on that. You can have secondary protection given the importance of the equipment that you're protecting. And understand this, students. Understand this. Very important principle. It is usual. It's a usual case that the equipment that you are protecting is much more expensive than the protection system. So the protection system can be elaborate and expensive, but usually it is protecting equipment that is significantly more expensive. Now, I suppose the addendum to that, yes, is that the process, yes, that you are maintaining may be important enough to warrant the implementation of an expensive protection system. Do you get that? So one, it can be the cost of the equipment you're protecting, but two, it can be the importance of the process that you are trying to maintain. You can't allow it to fail, okay? And therefore you need the protection as part of that. Okay, so I mentioned it before, but we'll just wrap up with it. All right. You can deliberately put in your backup protection, yes, while some protection schemes, and these that I mentioned here, the overcurrent and the distance, yeah, they provide, they come with inherent backup, but they are primarily applied to utilities, yes? Yeah, that's utilities, okay? So your backup protection can be obtained as, you know, an inherent feature of the protection scheme, or you have to get additional equipment to put it in. But those that are sort of built in would be your overcurrent and your distance. Your overcurrent by virtue of what we call coordination, yes, overcurrent coordination. And of course, your distance would be for your transmission lines. And once you have the protection on the different lines, then it provides you with some backup protection. Okay? And finally for today, wow, I thought this was final. No, we should have something else. Okay. So for your unit schemes, remember I said that you can protect just your transformer, just your generator. Yes? You have to go there and set up backup. So for your as an example, as an example, your primary protection for your transformer, for your power transformer, is differential protection. That's a primary. But as backup, you have overcurrent. Right? So if the differential, which is looking at input and output, doesn't operate, then if you're having the current exceeding a certain value, yes, then that will operate. So you have the overcurrent as your backup protection. And so as part of unit schemes, you want to go and get independent backup. Yes. And note that the backup is usually slower than the primary, because what you want the primary to be there to do the work. All right, do the work that it was set up to undertake. All right, and I know I can say finally, right? So you don't, what this is saying, you really don't want to depend on some of the equipment that is used in the primary protection. All right, so some of the, I mean, things like your voltage transformers, you know, voltage transformers are very expensive. They can be as expensive as your power transformers. Okay, so you don't want to replicate those. But certainly you may want to use a different set of CTs. Yes. You may use, well, obviously you'd use different wiring. They are going to the same breaker. Remember the switch gear we're dealing with now, eh? They're going to the same breaker, so you go into the breaker on different contacts. And this helps to really keep the two systems separate, so that what may cause the first system to fail yes, would not be replicated in the backup, because it means that you'll just be back at square one. All right? So, ladies and gentlemen, that is a very lengthy introduction. The material is there in Schoology, so you can review it in your own time. Yeah. When we meet again, what we will do is to have a brief discussion on some relays. We briefly talk about some equipment protection. And then in terms of calculations, and you would have seen this on the exam paper I sent you yesterday. We will look at how to set a simple overcurrent relay. Right? Nothing fancy. We just look at one relay. So that's the only calculations that we'll have to do for this section of the module. Okay, that's it from me today. Any questions, any concerns, any comments? If not, then that's it.
Excuse me, sir.
Yes.
Is it safe to say that say for you, I heard you mention the VTs. When you mention a VTs, is it a case where the VTs work directly with your the relays?
All right. Yeah. Some relays require both a voltage and a current input to operate. For example, your distance relays, they measure the distance along the line by comparing the current and the voltage. So really and truly what they are measuring is impedance. Right? As a matter of fact, that's another name that the relays have. Right? So some relays require both a voltage and a current input to operate. And the voltage output from your VTs is a standard 110 volts phase to phase. So it's coming down from whatever transmission voltage you have to that 110. So the short answer to your question is that yes, they provide input to your relays.
Okay, sir. Thank you.
You're welcome, sir. All right. Well, thank you for your attention. I hope you had enough coffee. All right.
Sir, Dr. Isaacs,
Yes, sir.
when will this the assignment that you talked about earlier be
Yeah,
so
I will communicate that to you via message. I need to look carefully at your project. I don't want to crowd you too much. So I want to spread it across your project.
all right, sir, thank you.
All right, take care then.